Picture a high-performance sports car for a second. To really understand how a language like Java works, this is the perfect analogy. You see, Java's object-oriented programming structure, that's the intricate blueprint of the car itself. It's the chassis, the body, the overall design. But a car doesn't actually move without engine doing the physical, mechanical work. In Java, that engine is made entirely of operators. So today in this explainer, we're taking a journey straight into the mechanical heart of this language, focusing specifically on exactly how Java operators perform calculations, manipulate data, and actually drive the logic of our applications.
Okay, let's dive into our roadmap for today. We'll start with the Java OOP blueprint, then move down into the calculation engine, look at assigning and comparing values, unpack logic and Boolean operators, zoom into bit level and unary mechanics, and finish up with the order of operations. Let's get into it.
Starting right off with Section 1, the Java OOP blueprint. Because before we can tinker with the engine, we really need to understand the framework holding all of it together.
So object-oriented programming, or OOP for short, our source defines it as a programming paradigm based on wrapping data, which we call variables, and methods into objects and classes. Honestly, think of this as a highly structured software factory. Instead of just having random code floating around loosely, Java demands that absolutely everything is neatly packaged. And this packaging is crucial because it restricts direct access to our data, keeping our programs secure and way easier to maintain.
And there are four main pillars that make up this factory's structural rules. First, encapsulation, which hides our data using private variables, basically wrapping the data and methods into a single, safe unit. Then there's inheritance, allowing one class to acquire properties and methods from another, which is a massive win for code reusability. Polymorphism gives us this incredible flexibility where one interface can take on multiple implementations. And lastly, abstraction, which completely hides the complex implementation details and only exposes the essential functionality to the user. Now, this macro-level design is absolutely beautiful, but like we said, it's just the blueprint. It doesn't actually calculate anything yet.
That brings us to Section 2, the calculation engine. Let's actually look at the assembly line of our code.
Within all those Java classes and methods, we have our operators. The source material defines an operator exactly like this. It is a special symbol used to perform operations on variables and values. These are literally the gears, the pistons, the spark plugs of our code. Because without operators, our variables just sit there statically doing nothing. Operators are what physically transform the raw data inside our OOP factory.
Now, the most foundational of these are the arithmetic operators. You'll definitely recognize the standard math symbols here: addition, subtraction, multiplication, and division. They work exactly like you learned in grade school. But I want you to pay close attention to that bottom row, the modulus operator, represented by the percent sign. This one is incredibly important in programming. It doesn't give you a decimal or a fraction. Instead, it performs division and then specifically returns just the remainder. So if you ever need to know if a number is even or odd, or you need to cycle through a sequence, modulus is absolutely your go-to tool.
And this brilliantly illustrates what operators actually do in practice. Take a simple example from the source. Say we have an integer a assigned the value of 10, and an integer b assigned the value of 5. When we write a plus b, that addition operator physically takes those two separate pieces of raw data, runs the mathematical calculation, and spits out a concrete, brand new value, 15. The operator did all the heavy lifting.
Moving right along to Section 3, assigning and comparing values. This is where we look at how to actually store results and check them against one another.
Right, so once we calculate a value, we have to put it somewhere. Enter assignment operators. The most basic is just the standard equal sign, which assigns a value to a variable. But Java's smart. It gives us these highly efficient compound assignment operators, like plus equals or minus equals. For example, if our variable a is 10, writing a plus equals 5 tells Java to take that current value of a, add 5 to it, and instantly pack that new result, 15, right back into the variable a. It's doing the math and the storage all in one seamless, highly efficient step.
Now heads up, because here is one of the absolute biggest gotchas in programming, and a total classic technical interview trap. You have to know the difference here. A single equal sign is an assignment operator. It forces a value into a variable. A double equal sign is a comparison operator. It doesn't alter any data, it simply looks at two values and asks, are these exactly the same? Mixing these two up is a surefire way to completely break your code because you'll end up accidentally overwriting your data when all you meant to do was check it.
And that double equal sign is part of a broader group called relational or comparison operators.
This includes checking if something is not equal to, greater than, less than, or equal to, and so on. Really, think of these operators as the true decision makers on our assembly line. Whenever Java executes one of these comparisons, the result is always, without fail, a simple Boolean answer, just true or false.
But what happens when our program needs to make a much more complex decision? Let's check out Section 4, Logic and Boolean Operators.
Before we break this down, I want you to think about this explicit question directly from our sources. What is the actual difference between the double ampersand and the single ampersand in Java? Because they both seem to mean and, right? So why in the world does Java give us both?
Well, here's the answer, and here is exactly why this matters for writing fast code. The double ampersand is the logical AND operator. It uses this brilliant feature called short-circuit evaluation. If you have two conditions and the very first one evaluates to false, it just instantly stops. It knows the overall statement can't possibly be true anymore, so it doesn't even bother checking the second condition. It short circuits, saving precious processing power. The single ampersand, though, that's the bitwise AND operator. When used with Booleans, it stubbornly evaluates both conditions, no matter what. It literally forces the computer to do extra work even if the first condition already proved the whole thing false. So, the crucial point here is that this exact same logic applies over to the OR operators. The double pipe symbol is the logical OR. If the first condition is true, boom, it short circuits and stops, since only one condition needs to be true for an OR statement to pass. The single pipe is the bitwise OR, which relentlessly evaluates everything. Knowing when to use those logical short-circuiting operators is what makes your Java program significantly faster.
All right, let's zoom in even further. Section 5, Bit Level and Unary Mechanics. We are moving from macro math all the way down to manipulating raw binary.
First up, unary operators. These work on a single operand. The increment and decrement operators are heavily tested in interviews because timing is literally everything here. Look at the difference. When the plus signs come first, like plus plus a, that's a pre-increment. Java increases the value by 1 first and then uses that brand new value in the code. But when the plus signs come after, like a++, it's a post-increment. Java uses the current value in your code right now and only increments it in the background after the fact. It might seem like a tiny little detail, but the order here dictates exactly what data your program is working with at any given millisecond.
Now check out another fascinating micromechanic, the ternary operator. Look at this unique syntax. A condition, a question mark, value 1, a colon, and then value 2. It's basically a brilliant, time-saving shorthand replacement for bulky if-else statements. Instead of writing out 5 lines of code just to check a condition and assign a value, the ternary operator handles the whole shebang in one sleek single line.
And finally, down at the absolute micro level of our engine, we have our bitwise and shift operators. Now these guys don't look at numbers like 10 or 5, they look at the physical ones and zeros sitting in binary memory. They perform operations on the literal bits themselves, shifting them left or right across the memory registers. I mean, this is as close to the bare metal hardware as Java gets, physically moving data bits to run incredibly fast, low-level calculations. Okay, so we've got all these mechanical pieces now, right? From basic addition down to bitwise shifts. Let's hit Section 6, the order of operations, to see exactly how Java keeps them all from just crashing into each other.
Just like in high school algebra, Java has a very strict timeline of which operator gets to act first in any expression. We call this operator precedence. Priority 1 is always parentheses. Whatever is inside them gets calculated first, no matter what. Priority 2 goes to our unary operators, like those pre- and post increments we just talked about. Priority 3 gives us multiplication, division, and our good friend the modulus operator, which will always jump ahead of priority 4, simple addition and subtraction. Then priorities 5 and 6 are our relational decision makers. Without this strict rules of the road hierarchy, Java frankly wouldn't know how to reliably perform calculations, and our entire software factory would just grind to a halt.
Which brings us to our final thought for today. We started out looking at the grand, high-level blueprint of object-oriented programming, encapsulation, inheritance, polymorphism. But as we've seen, literally none of that architecture functions without the microscopic gears of operators doing the heavy lifting underneath. So how do these simple mathematical building blocks, these basic plus signs, logical ands, and bitwise shifts, actually allow us to design endlessly complex OOP architectures? It's because by combining these fundamental, perfectly ordered calculations, we can evaluate any logic, we can manipulate any data, and we can build absolutely anything we can imagine.
Thank you so much for joining me on this deep dive into the blueprint and the engine of Java. Keep exploring, and I'll see you in the next explainer.